So, good morning. Welcome to Krishna's classroom. In the last lecture, we explored the following problem. Namely, does there exist an uncountable subset of R whose Lebesgue measure is 0? And by constructing the so-called Cantor set, we proved that the Cantor set has this property. It is uncountable as well as its measure is equal to 0. The next question that we take up is the following. To recall that we defined the outer measure, then we defined what are called the measurable class of functions, and then we proved that the measurable class of functions denoted the measurable class of sets, the measurable class of sets script M form a what is called a sigma algebra. Now on this sigma algebra, M star, the outer measure, turns out to be a measure with remarkably the countable additivity property, which was not there for the outer measure. Okay. So abstractly we defined what measurable sets are, and we designated by script M. Now, how large is this script M? This was the question that we asked. Then we found that it is sufficiently large in the sense that all the open sets of R are in it, entire R is in it, empty set is in it, and the complement of every set in it is also a member of this class, and therefore all closed sets are there. Then we also, from what we have explored, follows that all countable intersection of open sets is called G delta. The G delta sets are in it. Then all countable union of closed sets are in it, which is designated by F sigma. So it is extremely large class of sets, right? So we worked out what exactly is there in script M. Still we do not know what kind of sets go into it, other than that these kind of sets are in it. Okay, that leaves some questions unanswered at that stage. One was that is script M as large as the set of all subsets of R? So we constructed a non-measurable subset of R and it dispelled the doubt in this regard. That means the script M is a proper subclass of the set of all subsets of R. That is what we concluded. Okay. Then we asked some little questions more to know more about it, and we could prove that all countable subsets of R are measurable and the measure is 0. Okay. Then of course one of the natural questions that would crop up at this stage is that suppose, does there exist any set which is not countable but having measure 0. This question we answered by constructing the so-called Cantor set, and the Cantor set on the interval 0, 1 is measurable, it is uncountable. So there exists an uncountable subset of R which is measurable and has measure 0. So that is the question that we have answered. Okay. So the next question that automatically comes up is regarding how large script M is. Because we have found that all the open sets are in it, all the closed sets are in it, F sigmas are in it, G deltas are in it, and in fact one can prove that all Borel sets are in it. What do we mean by Borel set? Borel set is essentially the smallest sigma algebra that contains all the open sets. Okay, and so all Borel sets are belong to the measurement. Now this we could prove, and I said what Borel sets are. So this is a large class still. But now naturally the question is, see, this is script M, this is B. Does there exist an element here? So the question is, set in M which is not a Borel set. This is the question that we are trying to explore. And if we could prove that there exists a set in M which is not a Borel set, then it shows that the collection of Borel sets is a proper subcollection of script M. So this is the scenario. So the all subsets, then the measurable class in the sense of Lebesgue, and then the Borel sets, which is the smallest sigma algebra which contains all the open sets. Okay, what is the significance of this? Why you are bothered about all the sigma algebra containing all open sets? Now you see, on the real line, there are several structures. There is the algebraic structure that you have, and then you have also the topological structure. The topological structure is provided by what are called open sets. Okay. Now, all topological questions can be discussed only if there is a topology on space, which is already there in a natural way on the real line, which we already know. Okay. See, it is desirable. So, we are bringing in another structure. That means a concept of a measure for subsets, and we ask in the sense in which we have defined how large is the class of measurable sets. This is the question that you are asking. And it is our desire that it is as large as possible, containing all meaningful sets, especially all the elements of the topology. Okay, so that you can easily talk about what is called the integral of continuous functions. Okay, I will come to the details of that later. Give some hints when we introduce the concept of integration, or even before that, we would be discussing what are called measurable functions. At that stage, I will make some more statements on this. So that's what we are after. And then you see that, if the definition of the topology, what are the prominent conditions that you have? It's a collection of subsets of R, okay, having the property that entire R is in this collection, the empty set is in this collection, and there are what are called open sets, which in this case come out of the concept of length for intervals. Okay. And you define open sets using open intervals in that case, in the concept of neighborhood systems. Okay. So you see that the properties of the open sets are that the collection of open sets form a topology. The collection of the so-called open sets form a topology if they are closed under arbitrary unions and finite intersections. Whereas in the definition of measurable class, what we demand is that it is closed under countable unions and countable intersections. Okay, so there is a slight difference between them. Therefore, you don't expect the two ideas to be identical. That's why in this case we get a larger collection of the so-called measurable sets than the smaller sigma algebra that contains open sets. But that serves a purpose. Okay. We will make comments about this again and again when we introduce what are called measurable sets, and later when we introduce the concept of integral. Then it will be very clear what we are at. So this script M is big enough to accommodate all reasonable functions, and under the integrable class. Okay. So that's what we are up to. Right. And on the real line, we work with several restrictions. When you go to general measure theory, you see that we are going to drop off that. We don't have such things like a topology on it, etc. But on the real line, we are developing a concept of measure which is consistent with the topological structure. That's what we are trying. And we have been extremely successful in this regard. I say we, the mathematicians. Yeah, okay. So, our question is to answer this. Do you have sets which are not Borel sets and measurable? Try to answer this. Now, this again needs some kind of a preliminary work. and we construct a fascinating function called the Cantor-Lebesgue. So the theme of this talk, that is today, is going to be to explain what exactly Cantor-Lebesgue function is. Okay. So let me define certain concepts. Definition. These are all routine things that you know. A real valued function on R on some set containing or on the entire R is said to be increasing. Which simply means we are using in the sense that it is non-decreasing. Okay? Or sometimes it is called non-decreasing. So whenever we say it's increasing, we mean it is non-decreasing. If f of u whenever was okay. Now it is said to be strictly increasing if v belonging to S, f u less than v implies that is the strict inequalities here. Here it is not strict inequality, but we will be mostly working on what are called non-decreasing functions or increasing functions. Sometimes strictly increasing is also called increasing. Okay, right? Right. Now we introduce the Cantor-Lebesgue. Constructs. Let us construct. The Cantor-Lebesgue function is a continuous function phi defined on the interval 0, 1 with some the following properties. First of all, greater than 0. 2, 5 is contiguous. 3, 5 is increasing. 5 is differentiable on all open intervals. Successively removed in the construction of cataset construction of in the construction of the cataset where the derivatives that means on these open sets the function is going to be not on these open sets, on each of the open intervals that constitute these open sets. Okay. So I think I should, yeah, on each of these open intervals that you remove, the function is a constant. Okay, so that the derivative is here. These are the properties. So let us formally define. We'll explore this function a bit and then we'll try to understand this. For each k, let OK be the union of disjoint intervals joint collection of, and give the number 2 to the power k minus 1 0, 1. In the process of construction of the Cantor set. So let us work it out. So let O1 denote open interval 1 by 3 and O2. Now this is of course the middle 1/3 that we give out here. 1/3, 2/3. This is the open interval that we are giving out. The first stage. Okay. Now in the second stage, three by 3 square, that is 1 by 3, and 6 by square, and then you have 7 by square, 8 by 56. Okay, that is 1 by 9, 2 by 9, 1 by 3 to 2 by 3, and this is the interval that is already there in O1. So O1 is there, is inside this connection. We'll write it. See that. The open interval is already a participant in this. Now you see that the O2 is a bigger open set. So you have in fact O2 is a bigger open set and O1 is a part. Okay. Now what we do? So this is essentially just find out what exactly it is. At each stage, let us check this. This is something that we left out. Open interval is what we left out. Then what you are doing is this is 0, 1. We are dropping the middle 1/3 and dropping the middle 1/3. So this is actually 1 by 9, 2 by 9, this is 3 by 9, and this is 6 by 9, and this is 7 by 9, 8 by 9. These three open sub-intervals. So this is already a part. Okay. Now we will write down the general. Therefore, these are the O1, O2, etc. Now, and then what you do? What is the next stage? O3, we divide this. See, these closed intervals are the leftover. So we will take the middle one third and drop. This is the process to be called this one while constructing this, and refine it further and further using the process of middle, dropping the middle one third open interval from each of the closed components. Okay, so what you thus we obtain we use this notation Ck to be okay, and then define. See, what you have is that before that you have this property that OK plus 1. Okay. Therefore, you have Ck plus 1. So this is an increasing sequence of open sets, and this is a decreasing sequence of sets. This is what it is. Okay. Now, therefore, eventually C is equal to the Cantor set C is equal to intersection K equal to 1 to infinity Ck. This is also equal to 0 1 slash union now this is the definition of the Cantor set. I will, while defining the Lebesgue Cantor-Lebesgue function, now this is the Cantor set. Now on each of this we will define the function as follows. So that's the setup that you have. Now we are in a position to define the Cantor-Lebesgue. Follows. It's number K. Define as follows. To be the increasing function taking constant values on each of the 2 to the power k minus 1 open intervals that constitute constituting the open set of okay. Now so there are 2 to the power k minus 1 open intervals. So the function phi takes one by 2 power k, 2 by power k. Respective on the first second etc. open intervals constitute okay. So let us that is on the jth component okay. See, this is actually for k is j 2 to the power k minus so, and on ij j divided by this is the setup that you have, and it will be clear when we really work on this. Okay, let us explore this. So for k equal to 1, what is that you have? You have O1. O1. What is O1? O1 is the open interval 1 by 3. So on O1, define the function to be 1 by 2 to the power k. K is in this case 1, therefore define that means this is what you have. The picture that emerges So you are taking the interval 0, 1, then maximum value it takes. Okay. You have 1 by 3, 2 by 3. This is the open interval that you have. And on this open interval, the function takes the value of this corresponds to, so this is y. Rest we will say what it comes out. So that is the first stage. The second stage is we go to O2. We are going to work it out on. So successively it will be clear how you go about doing it. So O2 is essentially union 6 by 7 by 3. Okay. So what is it? This is right. See on 0, 1. This is 1 by 3. That is the one that we remove. And then we remove the middle one. This is 1 by 9 by 9. And then we remove 7 by 9, 8 by 9. These are the three intervals that consume. Now what you have is, so this is the case where k equal to 2. So you have 1 by 2 to the power k. So you define here the function as 1 by 4. So again you have, this is 1, so this is half, this is 1/4, this is 3. So the function takes the value 1/4 on this part, this interval. Now its graph is, see, on this portion it's going to be 1 by 2, and on this portion it is going to be 3 by 4. There it is. So the function takes the value 1 by 4 here. This is by x. So this is the graph on what you call O2. Okay. Now we go to the next level. In the next level, that we will stop by pictures, and the rest you can project. So I'm just doing this to give you an idea what this function looks like or how it appears and how this function is considered. It's a very fascinating function, and it eventually adds up to give you a continuous function. So let us take the case k equal to 3. K equal to 3, you see that there is a subdivision on this 0 to 1 by 9. So what happens is there you remove the middle one third. So this is what you have. This is 0 to 1. Already removed. Third. This is the one that we removed in the first stage. Now we removed the middle one third of this closed interval. And here also we removed the middle one third in the second stage. So this is from 1 by 9, 2 by 9, then 7 by 9, 8 by. This is what we have seen in the previous picture. Now what we do? At the stage 3, we remove the one third, middle one third of this. Middle one third of this would be from 1 by 27 to 2 by 7. That means 1 by 3 cube to 2 by 3 cube. So this is somewhere in that. Then here this is going to be 8 by 7 by 3 cube by 3 cube, 8 by 3 cube, and then you have this interval. So 3 cube, so 3 square is 9 by 3 cube, and 2 into 9, 18 by 3 cube, and then you have 19 by, and this is 20 by this we remove. Further the middle one third of this to be 25 by 3 cube to 26 by. What are the values the function takes here? So you have got the following set. You have is this O3 equal to 6 by union 7 by 8 by 8. Then you have this middle one, that is going to be 9 by 3 cube 18 by, that is this interval. Then you have 19 by 3 cube, 20 by union, 21 by 3, 24 by, then union 25 by union, this is what you have removed from the interval 0, 1. And what are the values that you give here? It is 1 by 2 to the power k. So when k equal to 3, it is 1 by 2 to the power k. 1 by 2 to the power k takes the value 1 by 8, then 1 by 4 here. That is the one that we gave already there. Then this is so this is actually 2 by 8. 2 by 8, and this is going to be 3 by 8, and this is going to be 4 by 8, and here 5 by 8, and 6 by 8 here, and 7 by, this is the disposition method. So what you have, this is 0, 1, somewhere here half, then 1/4, then 3/4, then 1 by 8, by 8, 3 by 8, 4 by 8, then this is 6 by 8, 5 by 8, 6 by 8, 7 by 1, 4, 6, 7. 2 to the power k minus 1. Okay, so these are the values that it gives. And the graph would look something like this. See, on this interval, it is going to be this one. On this interval, it's a constant, 1 by 4. And on this interval, it's going to be the graph, and on this interval it is going to be, okay, and on this interval it is going to be 5 by 8. This is 5 by 8, and on this interval this is going to be 3/4. So fourth, and on this interval This is where and on this, see, this is the way in which the graph grows. Okay, now you can easily see that as k increases, you see that the leftover closed intervals will start get defined and you will get the step function emerging. So it's an increasing function. Only thing that is not clear at this stage is why it is continuous. That is because the continuous refinement that goes on for these closed intervals by removing the middle one third, etc. So as k increases, now you see that you will get very dotted steps going up. Okay, so eventually you will have a functions coming from 0 all the way. It will be there. These are now steps that are fixed, and new steps will start emerging here. They are going to be on some open intervals. They are going to be constant functions as defined by us. So this gives you a picture of what this function looks like. Okay, I don't think I have to explain it anymore. Details. Now phi is defined as constant function on these intervals. What next? So we have not defined function elsewhere. So let us do that. So we define set equal to 0 and then define equal to supremum of phi t, where t belongs to O. O is the intersection of all these, the union of all these OKs. Okay, therefore O intersection for x belonging to C, that is the Cantor set, slash 0 we have defined. This is the definition of the Cantor set. The first and important foremost thing is to understand the structure of the Cantor set and the definition of this Cantor's Lebesgue. So you know exactly how it is working. Okay. Right? Now if you want to know what the value of the function is at some point x, what you do is take the interval O intersect with 0x. Okay. If it is going to be, if x is going to be inside some O, okay for something, then it's take the corresponding value. Okay. Otherwise, what happens is you will get the supreme. It's on the fringe of it. Then you are going to get supreme outcome. Okay. So note that phi is the supremum x. So this is the structure of the function. Okay, once you understand this function, we can now work further on this. So now we prove the properties of this particular function, and that's what is expected in this lecture. Okay, so we'll write down the theorem. I hope all of you have followed the, the construction of this function. It needs little bit of doing this kind of activity to understand it, rather than just take the definition, look at it. So you have to explore it. Only if you explore it, you will see what is the philosophy which leads to its definition. The Cantor-Lebesgue function is an increasing that means non-decreasing continuous function that means or I'll write it non-decreasing bracket decreasing sense maybe constants on some question. Non-decreasing continuous function which maps zero one onto zero. Its derivative exists on O, the complement of the Cantor set C where phi derivative 0, that is and also measure of O, that means the measure of, you already seen the measure of C is 0. So this is clear on that. Okay. Now it is quite easy work. Phi is orthogonal, non-decreasing on, that's clear. Therefore, its extension to the entire 0 1 is also. See the successive definition. So this is the definition of a function. You can easily see that this is increasing. So it's an increasing function. Now phi is continuous. Why it is continuous or no? Because on each of the component open intervals, it's a constant. Okay? Therefore, what happens if you take a point in O, it is in one of the open interval. Okay. Therefore, you can find a neighborhood of that point in which the function is a constant. Therefore, it is continuous at 0. That is, x belongs to O, where x is an interval, open interval, open interval O, x belongs that is x belongs to I for some open interval. Where phi is a constant. Now, because I is open, I open of x belonging to I. Rather contained in that means you have some epsilon positive for which x minus epsilon to x plus epsilon is contained in I. And there the function is a constant. Therefore, it's continuous at the point x. That is That proves the continuity of phi on O. But that does not complete this. Now, what happens on O? So, what happens on for instance? Okay, so let us take this. So we take x naught not equal to 0 or 1. 0 comma 1. That means at the end points we avoid. So x naught belongs to C implies x naught does not belong to 2 to the power k minus 1 open intervals removed at the stage k only at the stage k in the first k stages of the construction. So it is actually not in any one of these removed intervals. So what happens is that x naught does not belong to what happens is that x naught lies between two successive open intervals removed. Okay. Let me just try to figure it. So the situation is something like this is your x naught. Now this is an open interval removed. This is also an open interval removed. This is at the kth stage. So this is a part of OK. This is also a part of OK. So this is in between these two stages. If you want, you can call this AK and BK. So x naught does not belong to AK, which is a contained in and x naught also does not belong to BK. Now what about this AK and BK will be something like J upon, so this is actually J upon 2 to the power k, the value of phi and on AK by x equal to j plus 1 by 2 for k on BK. And in between there is nothing because we are going to further do. Okay. Therefore, what happens? So choose AK belonging to BK, some point here. BK belonging to A. Then phi BK minus phi AK. This is equal to 1 upon 2. It's a difference of these two. Okay. Right? Now what you can do is, now we can choose K arbitrarily large and make this difference as small as the, okay, therefore you get continuity. Before that, thus phi fails to be jump discontinuity. Now since phi is increasing, and and this is the important part, increasing functions can have only jump discontinuity. Continue this, it follows that there is no jump discontinuity for this. So the only possibility is that phi is continuous at x. Only increasing functions can have jump discontinuity. It follows that phi is continuous at. So what have we proved? We have proved that on O, phi is continuous, on C also is continuous, and it is continuously extended. Therefore, and increasing on 0. Now, if x naught is an endpoint, say 0 or 1, we can make a similar argument about the continuity of phi at 0 and 1. Thus, phi is continuous and increasing now you see that phi is constant on each component open intervals of constituting therefore since these intervals are open intervals, it is always an integer. Okay? Open intervals every point of O is an interior point of some open intervals phi is a constant on each of these open intervals phi is differential each point of O now C has measures here. O and measure of implies now phi 0 is 0, phi 1 is 1, and phi is continuous on and increasing from intermediate value theorem. By maths onto that completes the proof of theorem. Okay, so we have successfully constructed what is called the Cantor-Lebesgue function. Now we are going to make use of this function to eventually prove that there exists a measurable set in R which is not a Borel set. Okay, so that's our goal. So thank you very much. Let us stop.